Yeah, hey, it's amazing to have two science people together on a live. So I thought maybe there's a chance to learn something. Do you have any ideas of other like cosmological models, like alternatives to the standard Big Bang? Is there something like like a real alternative, like not just like a rebounding universe,
Right. There was a steady
like
state theory, but that
yeah.
didn't really get any supporting evidence for that.
Yeah, but isn't
There's
there like
really
something?
no other theory or hypothesis that has supporting evidence.
Hmm. So, like, I mean, what about the CC? What is it? The confocal, cosmical, confocal. The what was the name that the Nobel Prize winner? The old guy who's also working on consciousness. He came up with his own model. It's a
Penrose?
cyclic. Penrose, yeah, Penrose. The confocal cyclic cosmology was that model, like where he kind of proposed there is sort of it's like the universe is like contracting and reborn, and it's basically based on a matrix of whatever, like 27 elements, and there's one element that if you leave that out, it's basically just a size, like a scalar, like the size element of things in the universe. If that's ignored, then you basically the expansion can be it's a bit counterintuitive, but even if something expands, it actually doesn't, in principle, change its geometrical properties. That's the confocal kind of component, as I understand it. So if you forget the size changes, he argues that there is sort of a cyclic, a recycling process, like the cosmos is born and reborn, like it expands, but it doesn't matter. Like it's at the end of that
Right.
expansion, there's a new one basically coming. It's not even contracting.
Yeah,
So
I
that's
mean, I'm
that's
reading it.
just
It says the universe iterates through infinite cycles. Um,
yeah.
I mean, I'm reading it and I don't know what any of it means. So,
So you have never heard of that one? It's I found it quite interesting actually, but it doesn't really change too much fundamentally because I mean it's still expanding and you know um,
That was really popular in the 70s and 80s until we measured that the universe is expanding faster. So Einstein thought it was a steady state until he saw the data from Edwin Hubble. And then everyone assumed that the universe would be slowing down its expansion because gravity would be pulling everything back together to get to a
mm,
steady state or a contraction called the Big Crunch. But then we measured the fact that the universe is expanding faster today than it has in the past. So there's no evidence that the universe will ever condense.
yeah. Do you know of any model that sort of doesn't presume a background, like a background independent? I think quantum loop theory is basically not assuming space and time, right? So like if there's something that doesn't, you know, um, assume that there's time and space to start with, but tries to describe it. I only know one or two. I was just wondering if you have ever heard of other models. Don't get a chance to talk to physicists much at the moment. So, something that can describe how space and time actually emerge, rather than just assuming it like general relativity does. So, or at least general relativity makes time and space a thing and flexible. But there's something underlying, like Stephen Wolfram's physics
all right,
project
can
basically
we
goes in that
let's
direction.
let Professor answer because you kind of asked a whole bunch of different things.
Yeah, well, they're related though.
So there's really no hypothesis today. String theory has tried, other people have tried to explain the universe using extra dimensions, but they can't make any predictions that are testable. For example, the only prediction string theory can make, you would need to harness the power of a black hole. It makes it untestable. So nobody's come up with a better model, but we're always open to a better model. And there's people, always cosmologists, working on them, but we haven't found a model that can make predictions like the current model.
Yeah. I thought a quantum loop theory made a prediction that like the speed of light depends on the frequency. Like
It's
like
not observable.
yeah, it wasn't confirmed. I think they measured it. There was this gamma ray stuff happening, and I think there was a chance to measure that, but it didn't quite work out, it seems.
Hence the whole point of, to create a better model, you have to predict the current universe and your new prediction. And no model has done that yet. Doesn't mean we have the best solution possible. We have the best solution we know of.
Yeah. I personally don't like it at all. Like at least, the time, like our host, what is it? Peter is your name? That, there was 380,000 years before the inflation. It just looks like pretty artificial. I mean, the idea that everything was compressed and, the whole mass was so concentrated, and that just doesn't make sense to me, to be honest. Like,
I mean, it doesn't really make sense to me either, but the data backs it up. We have an even distribution of matter everywhere in our universe, no matter where we look. The CMB, the differences in the temperatures in the CMB only fluctuate by like a 10,000th of a degree across the two extremes.
How old is the CMB actually? Is that like that's around 380,000 years old, isn't it? It's not.
Yeah,
it doesn't
after
go
the
back.
Big Bang, 300,000 years
So
after the Big Bang.
Yeah, exactly. So it's not really a sort of signature of what happened at the very beginning, like in the very early.
Well, that's not
years.
observable though.
Yeah,
Well,
that's
it
the
may
point.
become observable.
In the future, maybe, yeah.
Yeah, because we're going to be putting the gravitational waves from the Big Bang and neutrinos from the Big Bang. We're building detectors to detect these things. So we may have other ways to detect things before the cosmic microwave background radiation. And I want to just make one comment, and then I'll turn it back over to Peterson, is the universe is under no obligation to make it simple or for you to like it. We just observe what it's doing. It has no obligation to make it simple or pretty.
Yeah, but it's also, there's no reason to believe in something other than Occam's razor, like a simpler explanation, right? Like the simpler explanation would be.
But we can make predictions and we can predict what happens. Just because you don't think it's the simplest explanation, it's the one that fits the data. So Occam's razor is the simplest solution to a problem, not the simplest thing.
Yeah, it's also just a statistical thing. Occam's razor just says it's statistically most likely to be the preferred explanation, but.
Yeah, but do we really need the first 380,000 years to predict everything else? I don't think so. Like to me, it looks like it's just a big question mark that happened.
What does that even mean?
Well, we're just basically going backwards in time, and like you were just observing and we're just going backwards in time and assume that there was you just extrapolate backwards. There's no evidence that this really went all the way back to the year 000, whatever, how many zeros you want.
I mean, so the CMB was predicted, like we had our Big Bang model, and physicists figured out, okay, if this is the way things transpired, then what we should find is a microwave background radiation out there. It was predicted, like, I think in the 50s, like way before it was actually discovered.
What exactly
and then
is
it was
that?
discovered. So,
Yeah,
like in
I know, and it
science,
was
we make these predictions, and then when we find evidence that conforms with those predictions, that tells us that our model is most likely pretty accurate. So it's not like we
yeah,
looked
but
at the
what
CMB
exactly
and
was
then
that?
decided to build a model around it. It was completely the other way around.
Yeah, but like I said, the CMB is not really. I don't think I don't know too many details, but it doesn't look like it's telling much about those early years. Like, I mean, it basically just says that the wavelengths expand over time,
So
and
again,
there was a
no,
homogeneous distribution
there's a
of
lot more.
matter. But
Yes,
that's not.
that part's really
I mean, what are
important.
the assumptions to make it work? What are the?
So again, the assumption is the universe starts off as uh, not necessarily an actual singularity, but like the most like condensed and uniform imaginable thing because it's the entire universe crammed into an unimaginably small state. So once you take something like that and expand it, there isn't really very much room for variation. Now, because of inflation and gravity, it allowed for matter to coalesce into large scale structures like galaxies and galaxy clusters and superclusters. And on the local scale, those things look like space looks mostly empty to critters like us, but on the scale of the observable universe, the distribution of matter is actually extremely, extremely homogeneous, right? So the Big Bang isn't an explosion, but if we think about it like, I don't know, you make
You
like a
know,
balloon. Like
I find it
we're
very
gonna pop
confusing.
a balloon or something and we just put like little dots of paint around it where it's not
Mm.
uniform. Then when it blows up, those dots scatter out and you get like, you get big empty regions where there's nothing here and then there's some dots over here. But if the whole thing is just a crammed uniform as much as it can, then when it expands, you get a distribution of material that's very even everywhere. And that's precisely what the CMB looks like.
Well, it doesn't actually make logical sense to me. Like you know, if you say
Okay.
that there weren't really like matter clusters of matter at the very beginning, then how would you even notice an expansion of the universe? If everything expands like you imagine, like on that balloon, like where everything expands by the same
Well, the universe
percentage.
definitely is expanding in the current day. So why
But
wouldn't it?
yeah, but we can only see this because some parts are not expanding. Like if everything expands by
Wait,
the same
what?
percentage, you wouldn't.
No, the
Yeah,
whole
of
universe
course.
is expanding. What do you
No, no,
mean?
no, no. That's how would we know then? I mean,
Because everywhere we
What do you
point our
mean?
telescopes, we can measure the expansion of the universe. And the further away objects are from each other, the faster they're moving away from each other because
Yeah,
of the
but
expansion. So
that's
we
just
can only talk about
totally
the
unlogical.
observable
Sorry,
universe, not anything outside the observable universe.
but that doesn't make any sense to me, to be honest. Like,
Well,
I mean, can I just explain why?
Sure.
Yeah, if you say it's expanding, it must something must become bigger compared to something else, right?
no.
Like,
The entire universe uniformly expands.
yeah, but that can't be. You couldn't observe that if that's really the case. The way I
Yes, you
understand it,
can
I
because
think
there are
that.
things in the universe that are moving and we see them. The space between objects is expanding. That's what we mean by the universe
Nah,
is
I
expanding.
think that's very misleading. You're really confusing people. I think if you like
What?
there is
No, I'm
no.
not. This guy's an astronomer and he thinks that I'm explaining it pretty well.
Yeah, can I just bring up my point? You know, there's a logical contradiction. You don't need to be an astronomer just to see the logic. Like if you are measuring an expansion of the universe, you're observing like let's say the distance between two galaxies, so or all galaxies getting bigger, right? Like you have
Between
more.
galaxy clusters. I want to be specific here. Between
Yeah,
galaxy
exactly. Yeah,
clusters.
okay. Yeah, even
Not
better.
between galaxies, but galaxy
Yeah,
clusters.
here we go. Well, what I'm saying is our meter, our reference, the meter, right, or whatever, however you define length in terms of, some whatever, a fraction of
Sure.
the wavelength, whatever we have nowadays. So that meter is not expanding, right? I mean, it couldn't because otherwise we
No,
wouldn't observe an
space is
expansion.
growing.
Space expanding doesn't mean the
No, but
universe is
space is not.
expanding doesn't mean that
It's only
things are expanding. Like
look, it's
matter
it's
doesn't
only
inflate like a
expanding on the
balloon.
large scale. It's only expanding like you said, between galaxy
The
clusters.
the
Within a
whole
galaxy, within a person, nothing expands.
Of course not, because a person is made of matter. Nobody said matter expands. The space between objects expands. The space between objects that are close together doesn't. I mean, it expands, but gravity on small scales is stronger than that force, and so objects like the moon is getting farther away from Earth. It's not because the space between Earth and the moon is expanding. It's because there's different things going on, and the Andromeda Galaxy is heading towards us. But I thought space is expanding. It is,
but only large,
on very large scales. Again, you can't look at what's happening on very small scales and then say, like, it doesn't have to perfectly mirror what's going on at the large scale. For example, space is pretty much empty, but that's because we're looking at it at a scale that's inappropriate. When you look at space on the scale of like an observable universe, the distribution of matter is like the same everywhere.
Look, I think maybe I didn't explain it quite clearly. Let's assume this the balloon model. Like you have those galaxies like circles on the balloon, and you blow it up, right?
Sure.
Then you have the distances between the galaxies, the circles, is increasing by a certain percentage. Everything on the surface increases by the same percentage, right? As you blow it up.
Yes.
Is that okay? So that would also mean like if you live on the surface of the balloon, you have to define length somehow, right? So you measure a meter somewhere,
yep.
And if that meter is increased by the same percentage, if everything expands equally,
the meter doesn't get bigger. You're talking about objects getting bigger. We're talking about this. We're talking about space itself is expanding.
Well, what is an object? It's the same. It's the distance between atoms or molecules. Whether it's the distance between galaxies or
so we're talking about the distance between galaxy clusters, and we can measure that.
Yeah, but shouldn't the distance between molecules?
It is getting greater between galaxy clusters.
Yeah, but the question is the distance between on shorter length scales, is that the same?
No, because gravity, as Peterson said, is stronger than the expansion force.
Yeah.
For example, what's stronger, your bone or gravity? Your bones hold you up against gravity. So you can actually resist the gravitational force.
Yeah. So, and that's exactly what I said initially. Not everything expands because we have gravity holding things together. It's not just gravity, it's actually electric
expand.
Forces.
Like you can walk on a moving treadmill, right? Things can remain in place despite movement occurring. And galaxies and galaxy clusters and solar systems
can you have to
together despite space expanding.
How can the space between something expand, but it doesn't change the size? I don't know if that's what you're claiming. Like if the length between my feet and my head is not changing because whatever gravity or electric forces, whatever, holds it together, then that space is definitely not expanding. Otherwise, I would get longer, right?
Like the expansion, this can be calculated. I don't know how to do it off the top of my head. But the farther away something is from you, the faster it's expanding. We know that. Even if we take what you're saying for like the space between where my head is and where my feet are, the space there is expanding because the whole universe is expanding.
No, it's
if
not.
That's true,
that's a misunderstanding.
We could figure out how fast that expansion is, but that expansion would probably be insanely small because the expansion is greater the farther you are apart from something.
But the expansion, if we know for sure, it doesn't expand.
Okay,
otherwise we could
not. You keep making assertions as opposed to allowing us to explain. So to Peterson's example of his head, gravity, if one of his atoms on the top of his head tried to, because space was expanding even at a small rate, gravity would pull it back down, and that little expansion of space would be outside his head because the electrostatic force is stronger than the expansion. So it can't rip matter apart. It's not that strong. So space is expanding, but gravity holds things in place.
No, but that's a contradiction. That's unlogical.
No,
Sorry.
it's not.
How can that be a contradiction? There are multiple
No,
forces
no. Look. You're
at
making it.
play.
You're saying. Can I just explain what I mean? Because you're not talking about
Like,
what I'm saying.
can a fridge magnet hold itself to a fridge despite there being gravity?
Yeah, that's nothing to. I'm talking about the space
Yes,
problem.
and intermolecular forces and gravity and
How?
electrostatics or
Look.
whatever that can hold things like whatever this is together, despite the fact that the space around everything is expanding. There's no contradiction there.
Peterson, just listen to me carefully here. Like, what is the difference between two galaxies, or let's say two cosmological objects, and my head and my foot?
The
Like
size, the
these are,
scale.
yeah, exactly. It's just a scale. In principle, there's no difference. The space
You just
expands.
answered your own question. Do you stop and think about what you just answered?
Yeah, well, I know what so we know that the space between my head and my foot is not expanding because that's what we define as the length. We have a length scale. We have a definition of a meter. It used to be an ion meter, and that if that was expanding by the same percentage, we wouldn't be able to measure expansion
Space
of the universe.
expanding and objects in the universe expanding are two completely different things.
What is the difference between objects in the
One
universe?
is
Like
space
my
and
head
one
is an
is
object in the
regular
universe.
objects. One of those things is space-time, and one of those things is matter.
So the space between my head and my foot is not space-time.
The
You're saying it's something
the
different.
space that your
What is
body
that space? I mean,
occupies
that's the same
is part of
space-time as the.
space-time, and it's expanding, but it doesn't necessarily exert any force on you. Not that would be detectable because we are incredibly small, and the expansion of these things doesn't become noticeable until you start dealing with absurd distances.
Okay, but how can we,
So,
let's say that the universe
Sigma, let me
expands.
ask you a question. Are
Yeah,
you always occupying the same space you were at a second ago?
the same length. Yes.
No. I asked you a different question. Are you occupying the exact same space you were a second ago?
We don't know if ether exists.
No,
That's
the Earth is
controversial.
going around the sun, so you're always occupying different space.
Well, there is a theory. In theory, it could be that
So you don't
that
believe
space
the
can
Earth
move
goes
with.
around the sun?
No, but we could take space with us potentially. That's a little uncontroversial. That's making it just unnecessarily complicated.
No,
But I'm
because you're missing the point.
no, I don't think I'm missing the point. How can you measure an expansion if everything expands and your
We
reference
look at
needs to
redshift.
not yeah, but the redshift is compared to our definition of the meter, right? Like if you
No,
have a
no,
million
Not not
no.
really.
meters from
It's based on
between
the
two
wavelengths
planets,
that are
and
observed.
everything expands by the same percentage, your reference doesn't even notice that expansion. It's the same
Obviously,
division.
hold
If
on
it
a
divides
second.
the
Hold on a
distance between.
second. Do you know how we measure
Hold
distances
on, I
to
couldn't
distant
hear you
galaxies?
taking off.
Do you know how we measure distances to distant galaxies? Or are you assuming we're taking a tape measure out
Uh,
there?
well, you could as well take a tape measure, and I
No,
think it's
but
easier
do
if
you
you
know
actually
how
assume
we
just a
measure the
regular.
distance to distant galaxies? I asked a question.
Uh, well, I guess you just measure the redshift and
What is
and
redshift?
well, it's well, it's well, it's just the same as when you hear sound, the same effect you get the wavelength elongation with objects that move far away
Close
away
enough.
of you. Close enough, yeah. I mean, I'm trying to keep it simple. We have like lots of probably not physicists in here. So
Well,
yeah, I mean,
you're also speaking in what is not your first language, and you're doing a pretty good job of it. So,
oh, thank you.
can we go backwards for 1 second? So, does the space around you expand, like from your head to your feet? Yes, but how come you don't expand? So, I looked up what the rate of expansion is. and Nixie can correct me if my source is wrong here, but this says that the speed at which the universe expands, it depends on distance. The farther you are, the more expansion there's. This says 70 kilometers per second per megaparsec. So that's correct. So that's very fast. 70 kilometers per second is very fast, but a megaparsec is 30 million billion kilometers. That's an absurdly huge distance.
Look,
so
nobody doubts
if we take that expansion rate and the distance and we reduce both of, if we go from 30 million billion kilometers down to 1 meter, then whatever the reduction in scale of that is, which it would just be that number times 1,000. Because that many meters in a kilometer. So then take 70 kilometers per second and reduce the expansion rate by, that would be 30 billion, I think. So yes, the space around you is expanding, but it's expanding whatever 70 kilometers per second divided by 30 billion.
Exactly. That's
which is going to be a number that is so absurdly tiny that it would take eons for it to expand even 1 millimeter. Eons and eons and eons. But the expansion, it's not just the expansion. Also, there are forces between the atoms that make up you, that hold you together, despite the space around you getting bigger.
Yeah. I can't believe you don't see the problem in there. Analogy. Like,
by the way, can you just stop for a second, Sigma? I want to say you explained that really well. Thank you.
What do you mean I explained it well? I don't think you
explained what was going on really well.
Yeah. So what exactly?
So how many millimeters a second? How would you equate that to millimeters per second? Do the math. How many .000000001 millimeters per second?
No, look,
it would be less than the width. It would be less than the width.
I can't believe I'm talking to physicists. Just give it an
it'd be
letter.
Two.
Like
let's
call it the
constant to the negative 18th power.
Let's call it
meters per second.
K. Let's call it K.
1,000 for millimeters.
Why are you getting into numbers? You just need any number. The same number you divide.
Minutes, take it times 60 for hours.
Oh.
Take it times 24 for days.
You just answered your own question.
Take it times 365 for years. I'm still at 7 times 10 to the negative 8th power here.
It doesn't matter how big the number is, guys.
Yeah, no, it does. It does matter how big the number is. By the way, that's how science is done, is we use numbers.
Yes, and you divide by the same number. That's it's the same percentage. No matter how small the number is, you have to reduce your standard meter by the same number if space expands.
You don't. I can't anymore. I actually have a headache. I have an actual headache right now. Oh,
man, you explained that so well. I'm going to steal that.